Okay, so today we're going to continue our discussion of channel form and behavior, and we're going to talk primarily today about bed morphology at the reach scale. So again, if you remember back, reach scale is kind of tens to hundreds of meters of a stream that have kind of consistent morphology or consistent characteristics. So that's where we're going to be focusing most of our energy today. So one thing I want to talk about real quick, and this is just something that we use in river science, and it actually comes from river running, so kayaking and paddling, and it's what we call the bank designations. And so you'll hear me talk about today and in future, you'll hear me talk a lot about kind of right bank and left bank when we talk about kind of where a feature sits on the river. And so when we talk about that, we're talking about the idea that if we're in the river kind of and flowing downstream, which bank is on our left and which bank is on our right. And this just provides kind of a consistent kind of frame of reference for where things are in the river. So if I'm talking about something, a bar on the right bank, you kind of have to visualize in your head, if you were standing in the river and facing downstream, it would be on your right side. Okay. Same thing if I said it's on the left bank, it would be looking downstream on your left side. So I'll use these bank designations when we're talking about some of the features today and in future. So I just wanted to kind of point this out and give you guys a heads up on this. So today we're going to talk specifically about bed forms. And so these are specifically features that develop as sediment is eroded and deposited and transported in the bed of the stream. And so these develop over time, and especially if the channel's in equilibrium, okay, these bed forms will develop and kind of sustain themselves over many, many, many years. And so in this lecture, we're primarily going to be talking about gravel bedded or gravel cobble bedded streams. And so just to remind you, gravel bedded is when we have D50 above 2 millimeters, and gravel cobble is when we have a D50 above 32 millimeters. And then there is a small section on sand bed morphology too, and that's where we get D50s that are less than 2 millimeters. So the first type of bed form, okay, is usually at a fairly small scale, but you can have patches of these pebble clusters that dominate an entire stretch of river. And so pebble clusters are these kind of elongated patches of smaller gravel that's kind of trapped by an obstacle class. And so in the diagrams here, we can see that, if we look at this from the side view, sometimes we'll get larger kind of accumulations of bigger pieces of sediment, and then little pieces of sediment or sand or small gravels will kind of accumulate on the downstream end of these. Okay, and if we look at it from the top here, you can see those obstacle clasts here, and then this little patch of or cluster of pebbles or small gravel that kind of get trapped in the leeward side of the flow there. And there's different ways that this can kind of express itself in rivers in a lot of different ways, depending on the flow conditions and the sediment size. But there's a few here that I've pulled out of an article. And so there's things like we call upstream triangles, where the small pebbles are actually on the upstream side. Downstream triangles is what I'm showing in this top view here. You can get rings where you actually get, sediment gets, larger pieces of sediment get kind of collected into a little ring, and you get a little patch of finer grained sediment in between. A diamond formation is where you get kind of an upstream triangle and a downstream triangle. Parallel lines are actually fairly common, and this happens a lot when we get imbrication. A lot is where we get the kind of shingling of sediment in the stream. And then there can be, it's kind of more rare, I think, but this idea of a transverse line that actually goes across the flow. So a kind of a line of larger stones with smaller pebbles on either side of it. And so this is kind of the smallest little bed form that we usually think about in gravel bedded streams, are these little pebble clusters, and they're fairly common. Okay. The next bed form that we can get in gravel bedded streams are what we call gravel ribs. And so this is where we get coarser material gets transported downstream and forms a little bit of a line across the river. And so we get these slightly larger clasts that form a little bit of a mini baby step in the river. And so this black and white photo here on the left, or on the right, sorry, is kind of an illustration of that. You can see we've got these big clasts here, another big clast up here, and some bigger clasts, creating a little bit of a drop here, and so a little bit of whitewater. This isn't a step like we're going to talk about in just a second, but these are kind of little baby steps. They're not very tall, and one of the interesting things in certain gravel bedded streams, especially up in headwater streams, is that oftentimes you'll see these as kind of a repeating pattern of gravel ribs in the river. They can repeat depending on the sediment size between kind of 1 and 10 meters apart. And so if you see one of these, you likely see more of them in the river because it's a function of slope and sediment size and flow conditions that create these gravel ribs. Okay, the next bed form is a step. And so again, this tends to be in higher slope environments and with larger sediment size. And this is where we get kind of larger clasts or sometimes bedrock outcrops as well, forming little pools on the stream. And so these are, again, kind of sequenced, and they happen in sequence, usually between 1 and 10 meters apart. And, you know, we get this, we call it step pool morphology. So we get a little bit of a pool forming here. We get the sediment here that forms the step, and then another pool below that, and then another step, and then another pool below that. And you can see in this photo with a little bit of a higher flow that looks like a set of stair steps. So, you know, you can, if you were walking up, okay, you'd go up the step onto a tread, up the step onto a tread, up the step onto the next tread. But it's, you know, pool, step, pool, step, pool, step. And then here's just one more example of this, a little bit on a lower flow day. So you can quite clearly see the steps here are fairly substantial, with a pool here and a pool below it. Okay. And so we've talked a little bit about bars before when we talked about sediment transport, but there are kind of all the different types of bars are specifically bed forms. And so these are accumulations of sediment. Bars usually form in areas where we have kind of lower velocities in the channel, so that we're getting sediment deposition. And the interesting thing about bars is that they tend to kind of create little feedback loops on themselves, like we talked about in the last couple lectures. And so once a bar forms in the river in a low velocity section, that then affects the velocities around it and actually creates more low velocities generally, and recruits more sediment. And so we can actually grow the bar in a kind of little feedback loop. So usually once a bar gets started, it can either maintain itself or grow, because it's affecting the velocities around it, creating lower velocities and recruiting more and more sediment. So all the different types of bars here, we'll look at a few examples on the next couple of slides, but you know, longitudinal or mid-channel bars. We have things called transverse bars, which kind of span the entire channel and are big kind of wedges of sediment. Point bars are very commonly the lateral bars that form in meandering streams. You can get diagonal bars or cross-channel bars that kind of go from one bank to the other in kind of a long downstream kind of fashion. There's very often we get bars at tributary junctions, so where two streams come together, the velocities get kind of mixed up, and we get a lot of deposition in those areas, and I'll show you an example of that on the Cedar River here in just a minute. And then down at the bottom here, these two examples are kind of more in a sandbed stream, so you can get sand waves or large dunes, and we'll talk about those more in depth. But in sand-bedded streams, we get dune formation and these sand waves or sand sheets. that form kind of bar structures in sand-bedded streams. And then if we have larger sediment in our streams, generally we classify these things by their size. So, you know, if we have extremely large sediment, we can call it a boulder bar. If it's smaller sediment, we can call it a gravel bar. Or if it's, you know, sand sized, we can call it a sandbar. Okay, so generally we tend to classify these things and group them together based on their sediment size characteristics. Okay, so just some examples of some different bar morphologies. And so this is an example from, this is Birch Creek in Alaska. And this is just kind of a nice stark example of point bar morphology in a meandering stream. And so you can see the real light white sand and gravel probably bars here, and they're alternating as they go downstream. And so that's one interesting thing about a lot of bar morphology, is that it tends to alternate sides. So if you have a bar on one side, generally you're not going to have a bar on the other side until you have one on the opposite side. So they tend to alternate from side to side. And so you can see that going all the way downstream here, that the bars are alternating. Even through this straight section here in the middle, you can see we have a point bar here, but then we just have a series of small little lateral bars that kind of bounce back and forth before we get this next big point bar down at this next big curve down here. Okay, so speaking of alternating bars, even in places where we don't have floodplains and space for the river to kind of spread out and meander, we still often get bar formation, just because of the way that flow initiates and flow kind of happens in rivers. It's not uniform. It has little perturbations in it, and so we end up getting oftentimes bar formation even in straight streams. And so this is an example of the lower Rogue River in Oregon. And so you can see this is kind of trapped in by a real steep bedrock valley, but we're still getting these bars on either side of the channel, even though we don't have a lot of room to spread out and meander here. And so again, this is just from kind of differential velocities and slower velocities in certain parts of the river. And so again, you tend to get these bars that alternate sides. So you get one here, one on this side. So this would be the right bank, and then down on the left bank. And then you can just barely see another one down there on the right bank further down. Okay, this is an example of a cross-channel or diagonal bar. This is actually on the Little Turkey River in Iowa here, so up in the northeast. And so here we've got some very kind of wonky different morphologies happening. Okay, so this is a fairly straight section of stream, fairly low flow. But you can see upstream here on the left bank, they have one bar and then an alternate bar here on the right bank. And then across, coming across, you can see where the gravels here are kind of coarser. That's what we call a cross-channel bar. So that's leading from this bar on the right bank, and it's kind of a trail of sediment that kind of goes across the channel and eventually, ends up on a bar on the left bank right here out of the picture. So this is what we call a cross-channel bar. And these are actually fairly common in Iowa. If you've done any paddling, there's a lot of these kind of cross-channel bars that connect one bar with the next one downstream. Okay, so now we're going to look at some bars on the Cedar River. And for this link will take you to the Iowa Geographic Map Server. This is a service of Iowa State's GIS facility. And so this has a whole series of kind of recent aerial photography available online just to look at. And so over here on the right-hand side, you can see there's a whole list of kind of the most recent called orthophotographs or aerial photography. And this goes back to, I think, 2002. We have air photos in the state back to the 1930s, but they're not necessarily available online very easily. We can download them from various places, but just as an online viewer, this one just goes back to 2002. So we're going to zoom in on the north part of the Cedar River and kind of the place where we've been going back to up in kind of near Blackhawk Park, just because there's quite a few bars up here to look at. And so we're going to start right here. Okay, this is right at the boat launch and the archery range at Blackhawk Park. And so here, okay, the river's flowing here north to south or top to bottom. So you can see on the left bank here, there's a nice big, this is a big sand and gravel bar. Okay, and then if we go upstream, okay, a little bit, you can just barely see the hint underwater here of a little bit of a cross-channel sandbar. Okay, so there's a little bar upstream here, and then right in here you can see kind of the faint shadow of a cross-stream bar. And then if we go upstream further, we get into a nice kind of more meandering section, and we end up with a nice series of point bars, so on the insides of the meander bends. And then upstream, again, so another point bar here on this meander bend. This meander bend has kind of a long, kind of trailing lateral bar. And then once we get up a little bit further, okay, where we get the West Fork of the Cedar River, which is kind of the Shell Rock River and the West Fork, and the Cedar River coming together, you can see in this section where we've got these tributaries come together, we get a real kind of weird set of kind of mid-channel or longitudinal bars here where, again, the velocities are really changing a lot there. So we get a lot of sediment deposition kind of in the middle of the river rather than on the edges. But if we continue upstream on the Cedar towards Janesville, again, you can see this has a really nice set of huge sandbars. Again, they're alternating from left to right as we go up. So the Cedar River's got some really nice sandbars, especially further up. Once it gets further down, the flows are a little bit more regulated and not as, the sandbars aren't quite as pronounced. But one interesting thing, like I said, we can go back in time on here and actually try to look at some of these orthophotos from before, and we can start to look at change in the river. So this is this is the 2017 data, and then this is the 21 data. And so you can see that there's quite a bit of change in the bars here. So especially kind of down here, right at Cedar Wapsie Road. And so one of the reasons that there's some change there is that they've done some bridge construction there, and so they kind of disrupted the flow for a while, but you can see the pretty significant changes there. Okay, if we go back even further, okay, let's see if we can go back to, say, let's go back even further. Let's do 2008. Okay. So here we have a little bit of a higher flow, so we can't see the bars quite as well. Okay, but you can see there's definitely been change there over the last few years. Okay, here's 2005. Again, a little bit higher flow, so the bars are underwater. Let's look at 2002. Okay, so again, a little bit higher flow, but you know the bars are still there in the spots that we find them mostly. So we can, with a lot of confidence, say that this is a fairly stable river system. Okay, mostly at equilibrium here, because these bar positions aren't changing that much. They're growing and shrinking based on the years, but they're remaining relatively constant. Okay. So here's an example of a mid-channel bar. So this is a mid-channel gravel bar. This is on the Chetco River in southern Oregon. And so you can see the river's flowing kind of towards you. And so we get this, we call a split flow or a split channel flow around this mid-channel island here. So the water is actually going around the right side here and the left side over here. So creating this nice big patch of gravel in the middle of the channel. Okay, so the next thing we're going to talk about is the kind of most common bed morphology that we see in most gravel bedded streams with kind of moderate to low slopes. And this is a big chunk of streams throughout the US and throughout the world. And this riffle pool morphology is kind of, it's unique in the sense that it's ubiquitous, but the form is fairly consistent, and you can kind of see it just about everywhere you go. And so the idea here is that as the river's flowing and starts to meander, the velocities create kind of fast spots and slow spots, and we kind of scour out and deposit sediment in kind of as we go downstream. And so we form this riffle pool morphology, which is an alternating series of pools, which are deep and slow, that generally have finer sediment, and riffles, which are shallower and faster and have coarser sediment. And so it's usually just this alternating pattern of riffle pool, riffle pool, riffle pool, all the way kind of downstream through a reach. And so on the image here, okay, you can see that in this case, the water's flowing away from us. Okay, but you can see the difference in the kind of surface texture of the water. So we go from kind of calmer water here, which is the pool, to kind of rougher white water here, which is the riffle. And then downstream we get calmer water again, which is the next pool. Okay, so we get kind of this idea of a pool transitioning to a riffle into a pool, and then the next bed form downstream would be another riffle. Okay, just another example. This is, I don't even know where this is. I pulled this one off the internet randomly. Okay, but again, the surface texture of the water gives us an indication of the bed form. Okay, so we have a pool at the very top of the photo, and then a short riffle, and then a pool here, and then where the raft is right now is coming out of this kind of big long riffle, and then another pool right down here at the bottom of the photo. Okay, so this is fairly common, and if you've done any whitewater rafting or whitewater kayaking, you know, riffles are the rapids generally at higher flows. And so this is generally the type of morphology that we like to do recreation in as well. Okay. So when we look at riffles and pools, okay, generally if we look at them from the side, again, they have this kind of alternate pool riffle, pool riffle, pool riffle formation. And so you can see here, we go over a riffle, has kind of a shallower form, and then into a pool, which is nice and deep, okay? And then it crests up over the next riffle, and then we scour out the next pool, and then up over the next riffle, and scour out the next pool, okay? So again, just this alternating pattern of deeper, and then shallower, and then deeper and shallower. So in meandering streams, generally where you can find the pools and the riffles are, the pools tend to be in the bends of the river. Again, that's where kind of velocities are changing fairly rapidly, and so we get a lot of scouring of the pool, so we can actually dig deep pools in the bends. And then in the straight sections, we're depositing some of that sediment that we scour out of the pools to form the riffle. So the pools are in the bends, and the riffles are kind of in the straight parts in between the pools. And so one of the questions that often comes up is how does riffle pool form, or riffle pool morphology form? And this is a question that geomorphologists have been grappling with for a long time. It's kind of so ubiquitous across a lot of different types of rivers and a lot of different environments. And so there's got to be some fundamental reason why these form. And the short answer is that it's really the complex interactions between turbulence in the water, the complex velocity gradients in the stream, so where we have faster flows and where we have slower flows in meandering streams. There's a big component of differential sediment transport because of those velocity gradients. So when we transport stuff and when we don't transport stuff and when we're depositing stuff. And then another important aspect to these riffle pool systems is that it's not just the low flows and it's not just the high flows, it's the kind of interactions between high flows, you know, almost flood flows, and the low flows, and kind of that constant, you know, seasonal or annual cycle of flows gets us to this riffle pool morphology. And so, like I said, it's a fairly ubiquitous bed form around the world. And so a lot of research has been poured into how these things form. And the best answer is that it's complicated. there's a lot of things going on, and there's not a lot of kind of concrete. There are some concrete theories out there, but they don't always work in all places. Okay. So just to give you an idea of what kind of the typical cross sections, if we were to look at a riffle pool section, a riffle pool reach of a river looks like. So in the pool sections, we get this kind of big asymmetric pool. So up against the point bar on the inside, we get a fairly shallow slope going down into the deepest part of the pool, which is usually out by the cut bank of the river on the outside bend. Okay. And the deepest part of the pool usually corresponds with what we call the apex of the bend. So the kind of the farthest outside part of the bend. Okay. And then over the riffles, these tend to be more of a uniform depth, but fairly shallow. So we get this kind of uniform shallow flow in the riffles and this kind of big asymmetric pool at the meander bends. Okay. Okay, so we're going to take a fly through down an actual river. And so this is a river that I'm not sure I've shown you guys this yet, but this is some research that I've done with some colleagues in the UK. And this is some data that we collected using drone photography and to create the three-dimensional model that you see here. And the fun thing is that in certain clear water stream environments, we can actually get really, really high resolution bathymetry of the river. Now, it takes a lot of kind of data post-processing, but the point is that we can get really, really high resolution bathymetry measurements underneath the water simply from drone aerial photography. And so as we fly down this, okay, you'll see that the colors in the stream are related to the depth. So the cooler colors, the purples and blues, are kind of shallower. So usually, let's say, less than 40 centimeters. The greens are starting to get into mid depths, less than a meter, but more than 40 centimeters. And then once we get into the really warm colors there, the yellows and into the reds, we're over a meter deep. So this just gives you an idea of kind of what to look for as we're traveling downstream. But this is a fairly common meandering gravel bed stream with riffle pool morphology. And so as we go down, I'll kind of call out and point out the different sections here. And then maybe we'll jump back and look at some individual sections. So we're starting at the upstream end and we're going to be flying downstream. And so here you can see a little bit of a deeper section here, the greens and yellows. Okay, so that's our first pool. And then as we go downstream, you can see we're going to go up and get really shallow over this riffle. And then we're going to continue to go downstream from there. Okay, so we're going to fly over this riffle. Okay, we get a little shallow pool right here, and then a nice big riffle right there that's fairly shallow, and then a nice big deep pool along this meander bend. Okay, another short little riffle, and then a big deep pool right there. Okay, all through here. The next riffle, okay, and a fairly shallow pool around this bend. And there really isn't a riffle right there, but then another big pool around this end, and then a nice big riffle that leads out to the end of the research site that we were looking at. Okay. So again, if we jump back to kind of here, okay, so here is the pool, the greens, okay, but you can see how they go from greens to light blues to purples, so extremely shallow right here. Less than 10 centimeters deep. And then we go straight down into a nice big deep pool. And this is the deepest part of the section of the river that we were looking at. It's about 1.3 meters deep. Okay. And then if we go down a little bit further, okay, so a nice big pool here. And then you can see how it shallows up a lot through here. Okay, and so you can actually see that it gets almost to, we call this a zero depth flow, but it's just basically at the scale of the sediment. So really, really shallow through here. So this is a nice big riffle, and then down into that next pool down there. So riffle pools morphology doesn't have to be limited to meandering streams. Okay, we can actually get riffle pool sequences in straight channels as well. So like that Rogue River channel that I showed you before that has kind of steep bedrock banks that don't allow the river to meander, we can still get riffle pool morphology in straight channels. And it's the same kind of general mechanics, just without the meandering part. And this is kind of an interesting part of rivers, is that they generally want to flow from side to side in their channel. They don't want to just flow straight down the channel. And it's a lot of quirks about how, the velocities at the edges of the river are slower generally than they are in the middle, and that velocity gradient creates things called call it generally helical flow in the river. So it's not generally just a flow straight down the river. The flow kind of is a kind of a spinning, churning mess of turbulence and flow as we go downstream. And because of that, the river generally kind of flows kind of from side to side. So we get faster areas and slower areas as we go downstream. And that leads to this riffle pool morphology or alternating bar morphology like we saw in the Rogue River. And so we can get riffle pools in straight channels as well. Okay. And so to illustrate that, this is kind of a kind of progression of kind of a conceptual model of how that would happen. Okay, so in the top here, this is a straight channel. Okay, so the sides of the channel are along the are kind of here and here. Okay, and as we start to put flow through it, okay, we start to get this kind of differential velocities and some sediment deposition, and so we start to build up some little bars. Okay, and again, because of the feedback loops, those bars tend to affect the velocities even more. And so we get slower velocities here and faster velocities here, and then they alternate back and forth. And so we end up getting these, building up these big alternating bars, and then the alternating bars are affecting the velocities in such a way that we start to get riffles in between. Okay? And so eventually we will get riffle pool morphology from a straight channel. Okay? And so just to kind of highlight this, the YouTube link up here in the corner, okay, is a little demonstration from these are called stream tables. So this is a kind of sand bed, and they're pumping water from the left, okay, and it's flowing down through this little channel, and then there's a collection basin down off the screen on the right hand side. And so these stream tables are used to kind of experiment with different conditions and demonstrate how different river conditions form. And so you can think about these stream tables as kind of like a scaled river. So these are, usually on the order of kind of maybe a small table size stream table. But they're kind of meant for demonstration and for research, just to kind of figure out what's going on. And so the sediment in here is primarily sand, just for demonstration purposes, but it gives you an idea of kind of how water flows and how water starts to kind of change things in a kind of natural system. So we'll play this real quick. Okay, and so it's going to start out with a straight flow, and you'll see the water is kind of a blue tint. And as it goes, you'll see some pulses of some higher flows and some retractions for some lower flows. And you'll see how the river kind of starts to meander and develop into a meandering stream without any kind of external forcing. Okay, so here comes the water, but you can kind of see the sediment moving around in there, and we're already starting to get meander bends. Okay, and so you can even start to see kind of riffle pools, so pools in the bends, and then shallower sections in the riffles. And so this is a few seconds on a stream table with just water flowing over sand, and we get the shapes that we would naturally see in a river. Okay. And we'll look at some more of these stream table experiments probably next week when we talk about large woody debris. There's a good one from the company who makes these stream tables on log jams. But if you're interested on the kind of the playlist here for the company that makes these stream tables, there's lots of different kind of illustrations and lots of different simulations that they've done. So if you're interested, you can look through those. They're kind of fun to watch. Okay, so the last kind of bed form that we're going to talk about are sand bed forms. And so sand bed forms mimic the bed forms that we would see in sand dunes, okay, or in the air. So essentially what we're seeing here is the sand moving with the fluid, whether it be air or water, and we get reactions, or we get the similar bed forms that we would see in sand dunes, but just underwater. Okay. And so the typical bed forms that we see in rivers are either what we call ripples, sand ripples, which are less than 10 centimeters in height and are kind of spaced or have a wavelength of less than 1 meter. Okay. And then if we start to get bigger and bigger bed forms, we get into dune morphology, which is greater than 10 centimeters in height and a wavelength of more than 1 meter. Okay. And the way that these form is, again, same thing that we see in sand dunes, is that as water flows over sand, we're getting erosion on we call the head of the dune, or the headward side of the dune, and then that sediment gets kind of pulled up to the top of the dune, and then as it goes down the backside, the velocities change and we get deposition on the backside. And so this is how we get dune migration, is that we get erosion on the upstream side, deposition on the downstream side, and then we can get this kind of downstream kind of march or migration of dunes and ripples in a stream. Okay. So here's just a kind of breakdown of the different bed forms. So you can actually get at really, really low flows, you can get what we call a plain bed, so a flat sand bed. But once we start to increase the velocities and the strength of the flow, we start to get riffles. And then if we increase the flow strength even more, those riffles will start to transition into dunes, and then bigger dunes. And so again, just to kind of reiterate the kind of height and spacing of ripples versus dunes, this graph kind of illustrates that. So again, ripples are less than 10 centimeters in height and less than 1 meter spacing, and then dunes are basically everything above that. Okay. And dunes can take some fairly interesting shapes. Okay, you can get transverse dunes, you can get sinuous dunes, you can get lunate dunes. There's all different kinds of dune shapes that form in rivers. And so the type of dune does indicate how long the flow has been going and the strength of the flow. And in rivers, it's fairly common to see a variety of different dune types depending on where you are in the river. So just to kind of give you an example of some dunes and ripples. So on the left-hand side here, this is in Louisiana. So this is a river that's kind of dried out after a flood. And you can see the rivers flowing from towards you, okay? And so you can kind of see the dunes, okay? The lighter colors and the darker colors are kind of different size sediments. So a little bit coarser sediment on the ridges here and a little bit finer sediment down in the valleys. Okay. On the right-hand side here, this is the Niobrara River in Nebraska. Okay, lots of sand out there, just like we have here in Iowa. But you can definitely see the shadows of the dunes, and so this river is flowing again towards you. So you get the upstream side here, and then the darker areas, the shadowed areas, are the leeward side or the downstream side where we're getting deposition. And so if you took some time lapses of that, you'd likely see those dunes kind of migrating or marching downstream, which is kind of cool. Okay, other examples. again, different sizes of bed forms. So these are both from the Columbia River in Oregon, so down towards the coast where we transition into kind of more of a sand-bedded stream. But here's a pair of sunglasses for scale on these ripples. So the ripples are, again, fairly small but fairly frequent. And then over here on the right are some larger dunes. Okay, so you can kind of see that dune morphology. This is, I think, actually down where it becomes kind of tidally influenced. So we're getting a huge kind of tidal range with the river being influenced by the ocean. But these dunes are part of that river flow. Okay, the next thing, I'm going to just kind of reiterate the ideas of scale, because I know we've talked about this before, but it's important again. Okay, so just to kind of highlight some of the scale divisions that we use in river science. Okay, so generally we go from kind of the largest scale that we look at are ecoregions. So this is thousands of square kilometers, multiple watersheds. Okay. And then we can go down to individual watersheds that can be kind of tens to hundreds of square kilometers. And then we get down to the reach scale. And we've talked about reach scale before, but this is, again, kind of tens to hundreds of meters in a stretch of river that has fairly consistent morphology. Okay, and again, we tend to break reaches at where we get breaks in slope, so changes in slope, or tributary inputs where we get changes in morphology. Okay. Within a reach, we can actually start to look at individual channel units. Okay, so these are on the scale of kind of 1 to 10 meters, roughly. Okay, but a channel unit is, again, an individual riffle or an individual pool or an individual step. Okay, those are channel units, and so channel units make up reaches, reaches make up streams, streams make up watersheds. Okay, but then we can go down even a little bit further than that, and we'll talk about this kind of as we go, but there is a smaller unit than a channel unit, and these are generally what we call patches or biotopes. And so even within a channel unit, so within a pool, there are different areas in a pool that have specific ecological use. Sorry, I had a misspelling there. There we go. Okay. And so these patches are within channel units. And so within a channel unit, you can have several different patches or biotopes. Or even within a riffle, you can have a faster section and a slower section. So those are what we call patches or flow biotopes inside of different channel units. Okay. So the thing I'm going to end with here on the idea of bed morphology is the idea of river classification. So in river science, oftentimes, just like all things, we're prone to classifying things based on commonalities. And so a lot of the river classification schemes out there are based on reach scale morphology. Okay, again, it's that idea of consistent morphology along a fairly good chunk of the river. And the classification schemes are based on some common elements. So kind of what bed forms or bed units do we have? So riffle, pools, steps. What types of bars do we have? What's the dominant sediment size? What's the plan form? Is it straight, meandering, braided? Okay. All of those go into kind of classifying rivers and coming up with river classification schemes. So one of the questions is, why classify at all? If we have, names for all the bed forms and the bar types and the sediment sizes and the plan forms, why don't we just use those? And it's, that's a good point. We could just do that, but it's in our nature as humans to kind of classify and try to simplify things. And so classification really gives us kind of a structured way of describing conditions across different rivers. So, if I tell you that we have a riffle pool morphology in our river in England or the UK, and you only know about riffle pool morphology in the US, you can actually make some, you have a common language. You say, okay, well, I know about riffle pool morphology in the US. You're talking about riffle pool morphology in the UK, but they're basically the same. Okay, the rivers are operating at the same, with the same processes, have similar behaviors. Okay, we can generally consider that those two riffle pool sections might have similar ecology as well. Okay, at least at a very basic level. Okay, versus if I tell you about a boulder bedded stream, okay, or a step pool stream, and you don't have that where you are. Maybe you don't have a common language, but you've read about those, so you understand that. So this is a way of just coming up with a common language for describing different conditions across different rivers. So there's two main river classification schemes that are used. The first is what's called the Montgomery-Buffington classification system. And then there's a second one called the Rosgen classification system. And so if you go out and work in rivers, you'll likely come across both of these. Both were developed as kind of stream management tools and kind of rapid assessment tools. So the Montgomery-Buffington was developed by the state of Washington, primarily for watershed management. And it was just, again, a way to kind of come up with a way to describe rivers in common language, so that if we go out to different parts of Washington, in the state of Washington, when I say this is a riffle pool reach, and then we go to the southern part of the state, we can say that that's a riffle pool reach, and we know that they have similar process and similar mechanisms and similar landforms or bed forms. And so that was kind of the main drive behind the Montgomery-Buffington classification system. The Rosgen classification system was developed by one guy, Dave Rosgen, who worked for the U.S. Forest Service, and kind of decided to try to use this as a way to come up with kind of prescriptive management rules for different rivers throughout the western U.S. But both of these classification systems are kind of primarily geared towards small to medium-sized rivers. Once we get into large rivers, these don't really work as well. And large rivers have kind of slightly different classification schemes anyways. And the other kind of caveat with this is that both of these were developed in the western U.S., primarily for kind of mountainous environments and intermontane valleys. And so if you can take these river classification schemes and translate them to the Midwest or to the East Coast, but you might not have all of the different classifications, and there are some slight differences, especially once we get into the Midwest. There's definitely more sand-bedded streams and a lot of kind of cohesive beds that aren't really considered in these river classification schemes for the West. Okay, so the Montgomery-Buffington classification system really comes from kind of looking at streams in kind of a very ordered spatial fashion. So the way that the classifications go are from steep to flat sections of a stream. And so these kind of are named after the bed forms that exist there primarily. So we have what we call cascades reaches, which are kind of real steep, large sediment size, kind of cascades and rapid channel units. Then we get into step pool reaches, which are dominated by step pool units. So, coarser sediment, but smaller step pools. They actually have a classification for what we call plain bed reaches, which are kind of big, long, extended riffles between pools or with very few pools that tend to be in a little bit steeper environment. So we get these kind of shallow, thin flows. Then we get into proper riffle pool reaches or pool riffle reaches, either way. And then flatter, once we get a little bit flatter into more sand-bedded channels, we get into dune ripple morphology. And so in the literature that goes along with the Montgomery-Buffington classification system, they have a series of kind of diagrams to help kind of river assessment teams or river managers kind of, give you a picture book kind of way of describing the morphology of the stream. And so each one of these classes has kind of a top-down view and then a profile view from the side looking from upstream to downstream. And so this gives you an idea of that cascade reaches are kind of really rough, have a lot of big boulders. Okay, the flow is kind of below the biggest boulders for sure. And we get these small little pools, but it's just kind of a chaotic, cascading system. Step pool morphology tends to be a little bit more regular. So we get the steps, the larger sediment steps, and then the slightly larger pools. Okay, and then in a profile view there, you get the big steps, and then the pools, and then the step, and then the pool. Okay, plane bedded streams, again, have a fairly uniform depth and a fairly uniform cross-sectional kind of dimensions. We generally see these, again, in steeper areas, but you can consider plane bed is kind of like a big extended riffle, is the way to think about that. And then we get into riffle pool morphology, which we've talked about at length today. So, big deep pools with usually sandbars and then riffles in between the pools. And then getting down into kind of flatter terrain and sand-bedded systems where we get ripple dune morphology. Okay. And so if we were going to take this to, say, the Cedar River, okay, we're kind of, the Cedar River, at least upstream from Cedar Falls here, is mostly dune ripple morphology, okay, but is kind of a slight combination of pool riffle morphology as well. So it's kind of on the cusp of dune ripple and riffle pool, because there are some pretty big pools and some really kind of underdeveloped riffles. But then for large stretches, it's more kind of consistent dune ripple morphology. So the Cedar here in town and upstream is kind of a mix of two different classes. So we can't just say it's just riffle pool or only dune ripple, but it's kind of in between. So there are some in between classes that we can use. Okay. So this is just kind of a table kind of illustrating some of the different the classifications in the Montgomery-Buffington scheme. So again, you could use this as well if you wanted to look at kind of things like bed material and slope and pool spacing and the dominant channel units. Okay, and so you could use a kind of decision table like this to kind of say, okay, I've got mainly gravel, a lower slope, longer pool spacing. I'm in riffle pool morphology. Okay. So the Rosgen classification scheme is also kind of a reach scale classification system. This has a little bit more of a decision tree approach to it. So it's got kind of, and I'll show you the decision tree on the next slides. You start with kind of, is it have a single channel, or has it got multiple channels? And then what's the width and what's the slope? And this, you go through kind of a decision tree to get to what Rosgen calls a type. So there's 8 different types of streams. He calls them A through G. We'll talk about that in a minute, that they aren't, it's not kind of a consistent, A through G isn't necessarily like the Montgomery-Buffington, which is like steep to shallow. They're kind of random. And the Rosgen system is meant to be done kind of without going out in the field. You can do it from topo maps or aerial photography, okay? And the variables that it uses are things like valley form, channel slope, channel pattern, channel cross-sectional shapes. And then there is a second level that you can go into that's a little bit more specific, that does require some field work. And this level 2 classification is kind of what's commonly used in management, or for management and restoration. And so here's the kind of classification scheme for Rosgen. And so the top part, so where we get down to stream type, that's the level 1 classification. So kind of the top half of this is the level 1 classification, and then the bottom half is the we call the level 2 classifications. And so here you can see that this is the decision tree here. So you start at the top and you say, is it single thread or is it multiple channels? And so let's say is it single threaded, and then is it entrenched? And we'll talk about entrenchment ratios next week. But, you know, is it kind of deeper than it is wide, or is it moderately entrenched, or is it slightly entrenched? And then what's the width to depth ratio, and then what's the sinuosity, and that gets us to a, you know, so if we have a single threaded, entrenched, low width to depth ratio, low sinuosity stream, we have a type A stream. Now, the problem with this is that if I go out and tell you, well, this is a type A stream, you're going to actually have this decision tree to say, okay, well, that's a low sinuosity, low width to depth ratio, entrenched, single threaded stream. Okay, it's a complicated system. And then below that, into the level 2 classifications, there's, you know, it's based on slope range and channel material. And so, like, you know, I could throw out, I have an A4, A plus stream. Okay. Well, then you'd have to go to your chart and say, okay, an A4, A plus is a gravel bedded, steep, type A stream with low sinuosity, low width to depth ratio, and is entrenched. Okay, and so this is actually one of the biggest challenges with this system, is that it's not really intuitive. There's not any kind of, there's no spatial organization to the different stream types, and there's a lot of kind of confusion about all the different types of streams in this. Okay. And there are some pictures for kind of the different stream types in the Rosjan system. And I'll let you guys, you can look through these. But again, there's not really a lot of consistency amongst them. Okay. So the Rosjan system is widely used by the Forest Service since it was developed as a Forest Service project. It's also used by other federal agencies like the BLM. Some state governments have adopted it as well. So it is fairly common out in the world. The way that this system has been promoted is by the originator, Dave Rosjan, teaches short courses to people out in the field. Okay, so he's actually quit the U.S. Forest Service and actually has a consulting company that basically all he does is promote and teach his classification system. So Dave Rosjan also kind of teaches this as a basis for stream restoration design. And we'll talk about this more in restoration, but, you know, trying to, you know, how to, you know, basically he has prescriptions for, say, let's say you have a B stream and you want to get to an A stream. Here are the things that you can do. And I will say that this is not particularly popular as a classification system amongst most practicing kind of classically trained fluvial geomorphologists. And I have there's a whole slide on the next slide. If you're interested, I'll leave it there and you can read through some of the criticisms. But basically it's not very well organized, and it's not very well used, or it's not organized and complicated, and doesn't actually kind of conform to the way that we as geomorphologists generally think about streams. Again, it's mainly for management and sometimes used for stream restoration, but it's not a great system. I bring it up because it's popular in a lot of federal agencies and some state agencies, and so if you go out and work in rivers, you may hear about it, but it's definitely not the best classification system to use. Okay. So here's a whole laundry list of criticisms of Rosjan, but and you can pause and read through those if you like. But basically, in the West, the Montgomery-Buffington classification scheme is better. Rosjan is, you know, it's out there, but it's not great. So that's all for today.